Okay, this is the first part of this homework for the chapters on Lenz's law and AC circuits. In this figure, the magnetic field through the loop changes according to this function, this B 6t squared plus 7t, where B is in Tesla and t is in seconds. The radius of the loop is 1.5 centimeters and the resistor is 3 ohms. What is the magnitude of the EMF and what is the magnitude and the direction of the current? Okay, so first I need to find the area, so let's just go ahead and do that. So to find my area of this loop, it's equal to pi r squared. That's equal to pi times the radius, which is 1.5 centimeters, or 0.015 meters. That is equal to, let's see, 0.0007 square meters. All right, I also need to find dB dt, because I'm looking for EMF. Let me just sort of show you the big picture. I'm looking for EMF, which by Faraday's law is equal to the negative of the change in the flux in time. But remember that flux is equal to B times A. It's actually the dot product of B and A. So this d phi is going to equal to negative A dB dt. So I have A here. Now I need to find dB dt. dB dt, that's going to be the derivative of this function, which is going to be 12t plus 7. Right. Notice that at all times that this is a positive function. That tells me, or this function has a positive value, excuse me. So that means that the magnetic field is increasing. That'll be important when we find the direction. Right, so I can come down here and put these values in. I'm looking for it at 2 seconds, but let me just first put in my A. A was 0.0007 square meters, and then dB dt is going to be 12 times 2 seconds plus 7, and that has a value equal to 0.022. It's actually negative 0.022, but the negative just tells us the direction, and we need to use our right-hand rule and Lenz's law in order to determine the direction. So the EMF is 0.022 volts. That's the EMF provided by this changing magnetic field. Now we want to find the direction. So the magnitude of the EMF is 0.022 volts. Now I want to know the magnitude and the direction of the current. Well, let's see, the magnitude is easy. I have 3 ohms here, so I is equal to EMF over the resistance, so it's just 0.022 volts over 3 ohms. I don't have that written down, so let me see, 0.022 divided by 3 is 0.007 amps. Now I want to find the direction of it. That's the magnitude of that current. Now notice here that my magnetic field is into the page and it's increasing. So my magnetic field is in the negative K direction. Right. The magnetic field that is induced, or rather the current that is induced, will cause a magnetic field that opposes this. Because it's increasing, the magnetic field that's induced, I'm going to call this B induced, is going to be in the positive K direction. So my induced magnetic field in this coil of wire that's generated by this coil of wire is going to be the opposite direction of this increasing magnetic field. Go back to your notes on Lenz's law. We use Lenz's law to find the direction of this induced magnetic field. And then we do our right-hand rule like we had in the previous chapter on magnetic fields. We let our thumb go in the direction of the current in this loop, and our fingers give the direction of the magnetic field. So my current is going to flow in this direction. So it's going to be 0.007 amps in the counterclockwise direction. All right, step back through that. I want to find the EMF by Faraday's law. It's the equal to the change in the magnetic flux with respect to time. And to find that, we say the area times the magnetic field. Remember, magnetic flux is B dot A. In this case, B and A are both, well, let's see, they're parallel. So that cross product is just equal to A times B. And then I had to take the derivative of B with respect to t to find this function, and then plug in 2 seconds, and then I find my EMF. That's the magnitude of my EMF. And then I have to use Lenz's law to find the direction of this induced magnetic field. This is the magnetic field that's caused by the induced current in the loop of wire. So there is a current that's induced in this direction, in the counterclockwise direction, that causes this magnetic field that comes out of the page in the plus K direction. And that's how I determine this direction for the current. A square wire loop with 2 meter sides is perpendicular to the magnetic field as shown. 1/2 of the loop is in the B field, which varies with time according to this function, and the loop contains an ideal battery with equal 20 volts. What is the net EMF and the magnitude and the direction of the current? Let's see. I'm going to actually put in a resistance here, or let's say that the resistance of the wire is 2 ohms. The resistance for 1 turn of the wire is 2 ohms, and then we'll go from there. This is a little bit different because if you want to find the magnitude of the current, if there's no resistance, then your current is it's infinite, basically, right? So we have to have some amount of resistance. Okay, so just like we did before, we're looking for the EMF that's induced. To find that induced EMF, that's equal to negative d phi dt. So we need to find out how is this magnetic field, or how is this magnetic flux given by phi changing with time, and then that will equal to our EMF, our induced EMF. And once again, don't worry about this negative. In fact, I just won't even write it because that just has to do with the direction of the EMF, and we'll find that by looking at the at Lenz's law. Okay, so first thing to do is I know that phi is equal to B dot A. These are all vector quantities. B here is in the plus K direction, and A is also in the plus K direction. Remember, the A vector, the area vector, is a vector that comes out perpendicular to your shape. So here, as long as they're parallel or anti-parallel, then your dot product won't have that cosine theta term in it. All right, so I need to find my area. My area is the area of this square that's within the magnetic field. So I had a square that's 2 meters by 2 meters. So the area of the whole square is 4 square meters. And it's going to be 1/2 of that. 1/2 of 2 meters times 2 meters. Or you can think of it as the area of that triangle, which is 1/2 base times height. And that's just equal to 2 square meters. All right, so that's my area. Now I also need to find out what is my magnetic field, how is it changing with time, and I'm looking at a particular time. Well, let's see, what is my particular time? Oh, no, we'll see. So here my BT is this function, 0.0420 minus 0.087. If I take the derivative of that, I'm just going to get minus 0.87. So the magnetic field is changing at a constant rate that's equal to this negative 0.87. Notice here that the magnetic field is actually decreasing, which will be an important fact later when we actually find the direction. But let's go ahead and calculate the magnitude of the induced EMF. That induced EMF is equal to d phi dt. That's going to equal to A times dB dt. Remember, this term is my d phi. A times B is equal to my magnetic flux. So that's going to be 2 meters squared times negative 0.87. Actually, I'm just going to call it positive because I'm just looking for magnitudes here. And 2 times 0.87 is equal to 1.7 volts. All right, so that is the the magnitude of the induced EMF. Now I need to find out what is the direction of that EMF. Let me clean this up just a little bit. I don't need this triangle anymore. Let's go to a different color. Red is kind of harsh. Alright, so I'm looking. I know that I have this 1.7 volts, but I don't know which direction it's in, so I need to find the direction. Let's go back to this idea that the magnetic flux was decreasing. That means that the flux is also decreasing in magnitude. So, by Lenz's law, the induced B field is in the direction same direction as the originating B field. Look back at that Lenz's law. We had 4 different cases. All right, and in this case, I have a decreasing magnetic field. The magnetic field that's drawn here is decreasing, so the induced magnetic field is going to be in the same direction. All right, this is my induced magnetic field. Now, in order to induce a magnetic field like that, the EMF that's generated in this loop of wire is in that direction, in the counterclockwise direction. So this EMF drives a current in the counterclockwise direction, which I could represent this as another battery, if you would, by drawing a battery that looks like this. So these 2 batteries are both oriented in the same direction. That means that my net EMF, see, I have the induced EMF, which is 1.7 volts, in the same direction as the other EMF, which is 20 volts. So my net EMF is going to be 22 volts, 21.7 or 22 volts. All right, so that's the first part of the question. What is the net EMF? That's 22 volts. Now let's find the magnitude and direction of the current. And as I said, we're just going to pick one turn is 2 ohms, let's say. That means that the current is the EMF over the resistance. That's going to be 22 volts over the resistance, which is 2 ohms, or 11 amps. Right, so that's my current in this wire. I have part of the current that's induced by the changing magnetic field, and part of the current that's just caused by the battery that's operating in the circuit. Now what happens if I go to 10 turns of wire? Well, if I have 10 turns of wire, this increases by a factor of n. All right, so I'm going to have not 1.7, but now I will have 17 volts. So instead of 22, I will have 37 volts. All right, so when I calculate my new current, it will be 37 volts divided by 20 ohms, because I also increased the resistance by a factor of 10, because where I had one loop had 2 ohms of resistance, 10 loops will have 20 ohms of resistance. And I get a current that's equal to 1.85, or we'll call it just 2 amps. All right, so a couple of things you have to account for. You have to account for the changing magnetic flux here, because I increase this by a factor of n if I have 10 turns. That causes for a greater induced EMF, but it also causes for a greater resistance. Now, in practice, these coils have a very, very small resistance, so you would actually get a much greater current, right? Because your resistance would not increase that much. All right, what is the magnetic flux through the loop shown in this figure? So remember, magnetic flux, that's this phi, is equal to B dot dA. So if I imagine this area, I have this area right here. The area vector will have a direction in the plus k direction. it acts perpendicular to the area that you're looking at. But actually notice here that I have two different areas. I need to consider this section separately because the magnetic field is different, and this section separately because the magnetic field is different. Alright, so let's do this one first. I have B dot dA, taking the cross product of that, is equal to 2K, that's my magnetic field, dotted with the area. And if I have a 10 centimeter by 10 centimeter square, which is what I have, that has an area equal to 0.1 meters squared. And 0.1 meters squared is equal to, what, 0.01. Alright, so I have 2 times 0.01 square meters in the positive k direction. K dot k is equal to 1, so this is 0.02 Webers. Now, if I want to do the second section, so looking at this section now, I come over here and my B dot dA for this section is equal to, again, negative 1K. That's my magnetic field, dotted with 0.01 meters squared in the positive K direction. So that gives me a magnetic flux equal to negative 0.01 Webers. Now I just add those up because I want to know the magnetic flux through that total loop. So if I bring these two together, of course, I'll just do positive 0.02 plus a negative 0.01, and of course that's equal to positive 0.01 Webers. So that's my net magnetic flux, just the sum of those individual magnetic fluxes. Okay, let's see. We have an LR circuit. First of all, I just want to know what is the equilibrium current. That should be really simple. 6 amps. Hopefully it's simple. Hold on just a second. Okay, sorry about that. So here I have this LR circuit, and I want to know what is the equilibrium current. As I said, that should be really easy. It should be 6 amps. The reason is, remember, as your current is increasing, it goes from 0 up to 6 amps. This inductor impedes the flow of the current because you'll get a magnetic field, an increasing magnetic field in this inductor that will cause an EMF to go in this direction. But at some point, the changing nature of that magnetic field just goes down to 0. So here, the magnetic field in this inductor, so I can characterize as dB dt, this approaches 0. And when dB dt goes to 0, that means it no longer produces an EMF. So at some point, that inductor just becomes like a wire. It no longer generates a changing magnetic field, and so it no longer generates an EMF. So the equilibrium current occurs when that inductor acts like a piece of wire. And when it acts like a piece of wire, well, it's just a very simple circuit, 12 volts, 2 ohms, I equals V over R, or 6 amps. Now I want to know how long does it take to reach that current. Well, let's look at B. So if I think about this, I is equal to the EMF over R, that's my maximum current, times 1 minus e to the minus t over tau, where tau is the time constant of this circuit. It's equal to L over R, and in this case that's equal to 3/2 of a second. Now if I try putting in something, you can try doing this in your calculator. If I put in 6 amps equal to 6 amps equals to 1 minus e to the minus t over tau, you'll find that you get an error when you try to solve for t, right? Because this is an exponential function. If I plot I versus t, the graph looks like this, right? So it slowly approaches that 6 amps, but it never actually reaches it. So here you would get t is equal to infinity, that it would never actually reach 6 amps. So this is sort of a trick question because it never ever reaches 6 amps theoretically. But in practice, it does reach 6 amps. Now remember our capacitors where we had a time constant as well? it looked exactly like this, looking at the charge on a capacitor. And we said that after 10 tau, it's fully charged, right? The same is true here. After 10 tau, this function approaches its maximum value, and we can say for all practical purposes that it is at its maximum value. So at 10 tau, just like we have for capacitors back when capacitors were charging, 10 tau, which tau here is 3/2 of a second, so this is equal to 10 times 1.5 or 15 seconds. So let's try this now with 15 seconds. If I do I equals 6 amps times 1 minus e to the minus 15 over 1.5, I find that I is equal to, well, is equal to 6 amps, 5.99999 or whatever. Okay, so we can use that same general guideline that inductors will stop inducing an EMF after they have reached 10 times the inductive time constant tau L. All right, C, I want to know now how long does it take to reach 1/2 of this equilibrium current? So I'm looking for what is T equal when I equals 3 amps, because the maximum current is 6 amps. What does it equal when it's equal to 3 amps? So I just say 3 amps. Just looking at this expression right here, which you have on your equation sheet. 3 amps equals 6 amps times 1 minus e to the minus t over 1.5. You'll need to make sure that you can do this in your calculator. I have a 1/2 minus 1 equals negative e to the minus t over 1.5. This is negative 1/2 equals negative e to the minus t over 1.5. Get rid of that. I take the natural log of both sides. The natural log on this side just gets rid of this, and the natural log of 1/2 then is equal to negative t over 1.5. And so t is equal to the negative of 1.5 times the natural log of 1/2. If you put that in your calculator, you find that's 1.04 seconds. So that's the answer. Be able to solve this equation. Make sure that you can do that. Number 5. I will pick back up with number 5 in just a little bit. Okay, let's look at this Rlc circuit. Here I have a 3 millihenry inductor with a 1 microfarad capacitor, and it says that the capacitor is fully charged by a 12-volt battery. All that's saying is that I have a charge on this capacitor that's equal to 1 microfarad times 12 volts. So that means that it has 12 microcoulombs of charge. All right, and no current initially flows in the circuit. So basically, I've charged this capacitor and I've just hooked it up to this inductor. And I want to know a number of different things. First, I just want you to discuss how the energy on the capacitor and the inductor changes with time. Well, first of all, remember that energies, I have the energy stored by the electric field, that's in the capacitor, that's equal to 1/2 CV squared, or 1/2 Q squared over C. And then the energy that's stored by the magnetic field, that's in the inductor, that's equal to 1/2 Li squared. And so we talked about in class how this is sort of like the potential and the kinetic energy of a mass on a spring, that when the spring is fully extended out here, that it has all kinetic and no potential, or excuse me, all potential and no kinetic, and when it's at its equilibrium position, it has all kinetic and no potential. So in a similar way, we get this oscillation between magnetic field energy and electric field energy. Energy stored in the magnetic field in the inductor, and then energy stored by the electric field in the capacitor. And both of those, the maximum value for each of those are given as these, 1/2 Q squared over C and 1/2 Li squared for the inductor. So initially, for this part A, at t equals 0, all of the energy is stored in the electric field. And I know that because the charge is at its maximum. I have this maximum value. So initially, UE is maximum, and UB equals 0. UB equals 0 initially because the current equals 0. And then as time goes on, those trade back and forth. So if I were to plot these, I'm going to plot UE in blue, and UE initially is at maximum, and it's going to decrease and then go like this. All right, and now if I plot the UB, it's going to initially be 0, and let's see how it'll go. It'll go like this. All right, so at any one time I have a certain amount of energy. All right, that is this maximum value. So at this point it's all in, what is this? This is UB, and at these other points the energy is UE. So I'm interchanging this energy between electric field energy and magnetic field energy. Okay, what is the first instant that the current in the circuit is 0? So let's write out that function, so this is part B. The function for the current is I. Actually, I think I've been using a lowercase I here, so let me erase that. I, this is the current at any time, is equal to I max, that's the amplitude of the current, times sine omega t. All right, the current in the circuit will follow this sine function. And the instant that the current in the circuit is 0 occurs when omega t equals 0, because sine of 0 is 0, so omega t is equal to 0. And we can see that here actually in this energy, in this plot that I've drawn up here. Initially my current is 0 because the current is going to follow UB. UB, the energy stored by the magnetic field, will be at its maximum when the current's at its maximum, and it'll be 0 when the current is 0. So UB will follow the current. All right, so whenever omega t is equal to 0, that's when the current is equal to 0. And we can find that time. Well, actually, that time is easy, right? Because the first instance is just occurs when t equals 0, right? And that's when the current equals 0. The next instant, when I is equal to 0, when the circuit is equal to, when the current is equal to 0, occurs when omega t is equal to what? 2 pi. Or no, not 2 pi, pi. All right. The next instant occurs when it's equal to 2 pi, 3 pi, 4 pi, and on and on. If I think about this circuit going around in phase space, I get it occurs here and here and here and here and back and forth. So whenever that omega t function equals some integer value of pi is when the current is equal to 0. All right, but the first instant is when t equals 0. Let's see, when is the current at its maximum value? Let me clean this up. I'm going to pause this for just a second. All right, so for part C, if I want to know when the current is at its maximum value, the current is at its maximum value when I look at this, when omega t equals pi over 2. Because the sine of pi over 2 is equal to positive 1, and so that is when I have my maximum current. So to answer this question, I first need to know what omega is. Omega, for an LC circuit, is equal to the square root of 1 over LC. And so this is going to be the square root of 1 over L, which is 3 millihenries, 3 times 10 to the minus 3, times C, which is 1 microfarad, that's 1 times 10 to the minus 6. And that angular frequency let's see, I get 18257. I'll keep all those sig figs even though they're not really significant. This is in radians per second. So that is my omega, and so the time when my current is first at its maximum value is when 18,257 times t equals to pi over 2. So I just solved this for t, so I get, I just divide both sides, I get pi over 2 times 18,257. All right, so that time is 0.8 times 10 to the minus 5 seconds. That is the first instant when I get my maximum current. So if I'm plotting out my current here, current versus time, that is the instant right here. This is at t equal 8 times 10 to the minus 5 seconds. That's part C. Part D, what is the angular frequency for the oscillating current? All right, I've already answered that. That's that 18,257 radians per second. And then what is the charge and what is the current in the circuit at these particular times? So if I want to know the charge, I think this was E. And remember, this this part right here is D. I had to find the angular frequency already. If I want to know what is the charge, well, the charge is equal to the maximum charge, which I've already found, that's that 12 microcoulombs, times the cosine of omega t. Remember, the energies are going to switch back and forth. So when the inductor energy is its maximum, that means that the capacitor energy is at its minimum, or at 0 rather. So so the charge on the capacitor will be 0. So since the energy switch back and forth, that's why I have a sine function for the current and a cosine function for the charge. All right, so and also because it's the derivative. But all right, so here I want to know what is the charge at 2 seconds. So I just say Q is equal to 12 times 10 to the minus 6 times cosine of my omega, which is that 18,257 times 2 and I get 8.9 times 10 to the minus 6 coulombs. Let me make sure that I was in the right mode for that. Yeah, I'm in radian mode for that, so that is correct. 8.9 times 10 to the minus 6, or 8.9 microcoulombs. All right, and then for F, I want to know what is the current. So this is just I equals Im times sine omega t. And you do a similar thing here. I've already found my Im, I think, haven't I? Ah, I have not. So we'll need to do that first. I'm going to do that right here since we have these equations drawn out here. If I want to find my maximum current, I say that UE is equal to UB. I know that those two are equal. It's like saying the kinetic and the potential energies of a spring are equal. At their maximum, they're equal because they're conserved, and these are our field forces just like in that case. So I have conservative forces that act, so this energy is never actually lost. So I have this electric field energy is equal to the magnetic field energy, and I just say 1/2 Q squared over C equals 1/2 Li squared. And then I solve for I, and this is going to be I max. Those halves cancel out. I get Q squared over LC, square root of that. I know Q, it's 12 microcoulombs, and I know L and C, of course. Let's see, I think I've already calculated this. It is going to be 0.22 amps. So that is my maximum current, which you need to find part F. And now that I find part F, I just plug that in. So it's going to be 0.22 amps times sine of that 18,257 times 2 and I get 0.15 amps. So that's my current at 2 seconds, and I'm just using this function. Now all these functions you'll have on your equation sheet, so but you'll need to be able to apply them in the appropriate way, and also discuss how the energy is transferred back and forth between the inductor and the capacitor, back and forth, and it does that without any loss of energy, because these are just field forces. Now of course that won't be true with the LRC circuit, because now we'll have a resistor that will dissipate energy, and I think an LRC circuit, no, not quite. We'll come back to this in just a few minutes. I'm going to take a pause. Okay, well this problem number 6 is really very similar to the previous question. Considering this circuit, the switch is in position A for a long time, then it's flipped to position B. Oh, I'm sorry, I didn't have the A and B here, so this is A and this is B. So it's in position A for a long time. That means that the capacitor gets charged, and then it's flipped to position B. So what we have here really is a 6.2 microfarad capacitor and a 50 millihenry inductor, where the 6.2 microfarad capacitor is fully charged by a 34 volt battery. All right, so this is 54 millihenries, and the total charge on this capacitor we can find by the capacitance times the voltage. So Q is equal to CV. This is Q max. That's going to be 6.2 microfarads times my voltage, which is 34 volts. That's 211 microcoulombs. So that's my maximum charge. And I want to know the frequency, and I want to know the current amplitude. So first I want to know the frequency. What's that equal to? Well, my frequency, or excuse me, my omega, is my angular frequency, is equal to 2 pi times the frequency. So frequency is omega over 2 pi. So I want to find out what is my omega. And for an LR circuit, as we've already seen, we already did on the previous one, omega is equal to the square root of 1 over LC. That's the square root of 1 over 54 times 10 to the minus 3 henries, and 6.2 times 10 to the minus 6 farads. All right, so that is that gives me 1728. That's in radians per second. And now I want to take that and I'll convert it into hertz. So I'm going to have 1728 radians per second divided by 2 pi. You can sort of think of this as being in radians, so the radians cancel. If that helps you, you can think about it that way. And this is equal to 275 hertz. So the frequency of this circuit, as it goes back and forth, every second it's going to oscillate 275 times. The energies will oscillate, like we talked about before in the previous problem. Those energies go back and forth, back and forth. This is the rate at which those energies oscillate. So this is the answer to part A. In part B, I want to know what is the current amplitude. Work it the same way as we did before. We say that the magnetic energy, UB, is equal to UE. The magnetic energy is equal to the electric field energy. That's 1/2 Li squared equals 1/2 Q squared over C. Q squared over C. See, the halves cancel. I'm looking for I. So that is the square root of Q squared over LC, which is Q over the square root of LC. And if I do that, I get, let's see, what was Q? I found Q up here, 211 microcoulombs, so that's 211 times 10 to the minus 6 coulombs. The square root of L is 54 times 10 to the minus 3 henries times 6.2 microfarads, so times 10 to the minus 6 farads, and this is equal to my current of 0.36 amps. By the way, you could have done this slightly different way if you wanted. You could have said 1/2 Li squared equals 1/2 CV squared. right? That would have been the same way. And I'm looking for I square root of CV squared over L, which is V square root of C over L. And if you put in those values, you also get 0.36 amps. All right, this is just a different expression for the energy stored by a capacitor. Remember, because you substitute that Q equals CV into either one. Okay, that's number 6, and I'll come back for number 7. Okay, continuing on with number 7, I have a single loop circuit that has a 7.2 ohm resistor, a 12 Henry inductor, and a 3.2 microfarad capacitor. Initially, the capacitor is 6.2 microcoulombs and the current is 0. Calculate the charging capacitor in complete cycles later for n equal 5, 10, and 100. Okay, so first of all, we're dealing with a circuit that has a capacitor, an inductor, and a resistor. It looks like this. There's no battery, but at the very beginning, I have this capacitor charged with 6.2 microcoulombs. Now, as we know, if we think about the energy in this capacitor, or in particular, let's look at the charge on this capacitor. Right, it's going to start out big, and then it'll oscillate back and forth, just like we had with our Rlc circuit, where the energy oscillates back and forth between the inductor and the capacitor. But because of this resistor element, I'm going to get a dampened oscillation like this. So gradually it'll go away. Now, there are two functions that describe this charge. Q is a function of t, or rather, the function that describes the charge has two components. It's equal to my Q max. That's going to be my 6.2 microcoulombs times the exponential, which is e to the minus RT over 2L. This will be on your equation sheet, times the cosine of omega prime t. So what I want to know is what is the charge at particular times. Now, if I think about this, the charge, if I think about the period of this oscillation, because I'm looking for the period at these particular intervals, 5 periods, 10 periods, and 100 periods, that's going to occur. This is my 0th. 1 period is this time. So what I'm looking for is 5 times that time. So first I need to figure out what is that time, first of all, and then I can determine the times. But I also can realize that this term, which defines how this function oscillates back and forth, that I can just get rid of that, because at those times, at 5, 10, and 100 times the period of this cyclical function, that cosine term is always going to equal 1, because I'm always going to be at the peak of this cosine function. All right. So first thing, I just want to find out what is the period. So I also know that omega prime here is equal to omega squared minus R over 2L squared. And further, that omega is, like we've had already, that's 1 over root LC. Right, so I need to find out what omega prime is, because that's my angular frequency of this circuit. And then from that I can find the frequency and I can find the period. So let's just calculate what omega prime is. It's going to equal to 1 over LC minus R over 2L squared. I have all these values, so that's going to be 1 over 12 times 3.2 times 10 to the minus 6. That's 1 over LC minus R. Let's see, R is 7.2 ohms divided by 2L. And L was 12 henries. Right, so that gives me my angular frequency of the circuit, and I find that to be 161.4. It's in radians per second. However, I really need to know the period, because I'm looking for certain time intervals of the period. I also know that omega prime is equal to 2 pi f, actually to keep in our I'll have this prime. Remember, back when we derived this, there was a difference between omega and omega prime, but omega prime is still the angular frequency of this circuit. So I can solve this for F. That's going to be 161.4 over 2 pi, and I get the frequency. And actually, I don't know this value. It is what it is. I also want to know T. That's really what I want to know, which is 1 over the frequency. So that's going to be 2 pi over 161.4. That's really the number that I want to know, and that number is equal to 0.039 seconds. This is the period of the oscillation that occurs in this RLC damped circuit, these damped oscillations. Okay, so now I'm ready to calculate my charge, because I want to know what is the charge after 5 time intervals, after 5t. What is Q equal to? Q equals what after 5t? And so I just say Q is equal to 6.2 microcoulombs. That's my maximum charge times E to the minus RT over 2L. R is 7.2 ohms. T is going to be 5 times 0.039 seconds over, was it 2L? Sorry about that. 2 times, I think this was 12 henries. Yeah. Okay, so that's the exponential all to that e to this value. Let me make that more clear. So this is e raised to that power. Then I can calculate that charge. Remember that cosine function at t equal 5 at the time of 5 periods is equal to 1. So I'm just going to leave that out because it's equal to 1. It doesn't affect my answer. And I find 5.85 microcoulombs. I do the same thing for 10t and 100t. I'll just give you the numbers, but it's exactly the same, except you're going to change this to a 10 now. And here I get a charge equal to 5.52 microcoulombs. And finally at 100t, I get 1.92 microcoulombs. So remember this charge, I'll very likely ask you to plot this, by the way, just to sketch it out. This charge gradually gets smaller and smaller. It follows that exponential curve, and it oscillates back and forth, but the maximum gets smaller and smaller because of that exponential function within the charge expression. All right, so that's number 7. Number 8, I have a 50 ohm resistor connected with a AC power source. The amplitude of the EMF is 30 volts. What is the amplitude of alternating current if the frequency is 1 kilohertz or 8 kilohertz? Okay, well this is a very simple question because actually the current in a resistor is not affected by the frequency. So I is just simply E over R. So that's going to be 30 volts over 50 ohms or 0.6 amps. And that's regardless of the frequency, either 1 kilohertz or 8 kilohertz. Now, however, this would be a circuit that would look like this. However, if I had a circuit that looked like this, where instead I had a capacitor, this is not true. My current here is equal to E over the capacitive impedance, or the capacitive reactance, excuse me. The capacitive reactance, remember, is akin to our resistance, but instead of not being dependent upon the frequency, it is. The capacitive reactance is equal to 1 over omega d times C. So this then would be dependent upon the frequency. The higher the frequency, the higher the current that you would get in this circuit. And similarly, if I had a circuit that had an inductor like this, the current here is equal to the EMF divided by the inductive reactance, XL, but XL is equal to omega DL. So this is equal to the EMF divided by omega DL. So if omega increases, this current will go up. When omega increases here, this current goes up. And I misspoke before. When omega increases here, this current goes down. And with the resistor, when omega increases, this current remains the same. It's unaffected by the frequency of your EMF generator. And we'll do 9, and actually on number 9 we're going to not do part C, so you can just forget about part C. It was a little more complicated than I thought. Okay, so here I have this AC power supply, and it's connected to an inductor. And I want to know what is the maximum value of the current. Well, this is just like the problem we did before. I is equal to EM over the reactance of the inductor, the inductive reactance. So that is going to be equal to 25 volts. Remember, this XL is equal to omega DL, so that's going to be 377 radians per second times 12.7 henries. And that gives me the maximum current, which is 0.00522 amps. So that's part A, and I just use this idea. I remember XL is equal to omega DL. Now, when the current is at a maximum, what is the EMF of the generator? Okay, well, this is a little more complicated. When the current is max, its maximum value, that means that its derivative is 0. Because look, if we're looking at a plot of current versus time, I'm not going to worry about the phase shift, but if I just plot current versus time, the current is at its max here, and the derivative of this function at this point is equal to 0. So when it's at its max, the derivative of the current is 0. That's important because the EMF of the inductor is equal to di dt. And so if the derivative of the current function is 0, that means there's no EMF of the inductor. So that means that EL is equal to 0 volts. Now, however, EL and the EMF are 90 degrees out of phase. All right, so if I were to plot the phasor diagram, let's say this is EL over here. It's at 0. That means that E will be up there. It'll be at its maximum value because the separation between these is 90 degrees. So the generator then, at this point, when the current is at its max, when the current is at its maximum, the EMF of the generator is going to equal 25 volts. Okay, so looking here at problem number 10, be able to describe what these phasors are. Remember the phasor shows the magnitude and actually the phase of this oscillating function, the sinusoidal function, and the y component of the vector that we'll draw will represent the magnitude of that function. So for example, if I take this point right here, point A, notice that it has a positive value. So it has a positive value here on this axis, and it's also increasing. That's going to put A in the first quadrant because remember these phasors, they go in a counterclockwise direction at a rate omega t, whatever the phase of that function is, and so the y component of this vector gives the magnitude here, and as this vector moves around, it's going to increase its y component. Now if we look at B, it still has a positive magnitude, but it's decreasing. That's going to put B in the second quadrant, because as this vector moves in this direction, the y component of it will decrease just as it does here. Now C has a negative y component at its maximum. That means that C is going to be right here. It is on the y-axis, on the negative y-axis. Negative because this is in the negative part of the function. And then D over here, I have a I have the y component is positive, so it's going to be in this direction. So this is D. One I didn't ask, but I could have. Let me just go ahead and point it out here. What about, say, right here? This is going to be either on this axis or this axis. And notice that it is now increasing as I move in this direction, so that's going to put it on this axis. Because as this moves in this direction, the y component will increase and become positive, just as this function does. So if I call this E, E would be on the positive x-axis, the phasor. So be able to interpret these phasors. They're a really useful tool when you're combining, when you're trying to analyze, for example, an RLC circuit, as we've been doing, these oscillatory functions. And it could be something that you see again. You won't see it in PChem, but some of your engineering students might see phasors again, and hopefully you'll remember some of this. Let's look at this transformer. I have this transformer. It tells me that the primary voltage is 100 volts and that there are 4 turns of wire over here. And I want to know what is this voltage. And this is, there are 8 turns of wire here, all around this iron core, which is, it's a laminated iron core, so that electricity doesn't actually flow through the core, but you get this changing magnetic flux in the core due to the wires. Now, each turn of wire has the same EMF. Each turn here and each turn here, because they're both experiencing the same change in magnetic flux, so each turn of wire experiences the same EMF. So if this is my primary voltage, I'll call this VP, and over here this is going to be my secondary voltage. I can describe the EMF of a single turn of wire as either VP over NP, that's the number of coils, this is NP right here, the number of turns of wire, or the turn of wire can also be VS over NS, where this is NS. So I get VP over NP equals VS over NS, and here I'm looking for the secondary voltage, so I'm going to say VS is equal to VP over NP, or VP times NS over NP. So that's going to be VP, which is 100 volts. And now the question of is it a step up or a step down transformer is dependent upon the value of this ratio, and NS over NP is 8 over 4, which is 2. That makes this 200 volts. So that's my answer. That is my secondary voltage, and the second answer of this is a step up transformer. So if NS is bigger than NP, then it's a step up transformer, and if it's the opposite, it's a step down transformer. That is, if I had more coils over here, then I would have actually a drop in voltage. So if it was switched the other way around, it would be 100 volts and 50 volts. And let's see here, we'll do this last question. RLC circuit has a resistor of 100 ohms. Actually, I'm going to hold off and do this in just a little bit. Okay, this is question number 12. Lots of different parts to this question. First, I have an RLC circuit. It has a resistor of 100 ohms. It has an inductor of 200 millihenries. And a capacitor of 3 microfarads. And this is all driven as a forced oscillation, a forced circuit with an AC generator that operates at 24 volts at 60 hertz. That has a maximum EMF 24 volts at 60 hertz. First, I want to know what is the maximum initial current of the circuit. All right, so what is the maximum current? Actually, I say initial, but really just what is the maximum current of this circuit? Well, as with all my circuits, Ohm's law applies, but as you recall, I not only have the resistance of this resistor, but I also have the reactance of the inductor and the capacitor. So this current is going to equal to the maximum EMF divided by the impedance. The impedance, remember, we got from combining our phasor vectors, is equal to R squared plus XL minus XC squared. And that's equal to 24 over 100 squared plus 75.4. I'll show you this. Let me just go and write it. Actually, let me go ahead and do it down here. So XL is equal to omega DL, which is 2 pi f. That's omega times L. That's going to be 120 pi. It's 120 pi because I have 60 hertz times 2 pi is 120 pi times L, which is 0.2 henries. Right, 200 millihenries is 0.2 henries. And that has a value equal to 75.4 ohms. Further, I can find XC. It's 1 over omega DC. That's equal to 1 over 2 pi f C, 1 over 120 pi. That's my angular frequency. C is 3 microfarads. This has a value equal to 884 ohms. All right, so each of these has certain reactance. I can put that in here. I get 100 squared plus XL, which is 75.4, minus 884. That's squared, and take the square root of that. Now if I take this, I find that if I calculate that, the I max is equal to 0.03 amps. That's the maximum current that you get out of this circuit. Okay, now I also want to know what is the phase shift, because I can use the phase shift. If I know the maximum current, I know the phase shift, I can find the current at any particular time. So I want to find that phase shift. This comes about from our analysis of the phasors. Tan minus 1 XL minus XC over R. Remember, this is just simple vector math here. This is 75. Inverse tan of 75.4 minus 884 divided by 100 ohms, and that is equal to minus 1.45 radians. That's my phase shift, and I can use that now that I know the maximum current and the phase shift. I know the function, which is on your equation sheet, is equal to I sine omega dt minus phi. This is my function for the current in this circuit. That's going to be 0.03 amps sine 120 pi t minus my phase shift, which is going to be plus 1.45. And so that tells me my current. If I put that in for part or that's part C, rather just writing that expression. And then for part D, if I want to know this at t equal 0.1 seconds, I just plug in 0.1 here for t, and I find that the current is 0.0298. So it's actually really close to my maximum current. So at 0.1 seconds, I'm right at the peak of the current. Okay, so that's my current at 0.1 seconds. Then I want to draw the phasors. Remember, just in general, be able to draw the phasors for these circuits. And remember that the inductance VL, the VL for the inductor, the voltage for the inductor, always leads the voltage for the resistor. And the capacitance voltage, VC, always lags. Remember that we had this mnemonic, Eli, the Iceman. All right, our current is always going to be in the same direction as VR. That's going to be our current. And the EMF of the inductor will always lead the current. So this is the EMF of the inductor. The EMF, that's what the E means. L means the inductor. I is the current. The EMF of the inductor is always going to come first. And the EMF of the capacitor is always going to come after the current. So this green represents the current. And the EMF of the inductor always leads. The EMF of the capacitor always lags. And then finally, what is the resonant frequency? Well, the resonant frequency is just equal to 1 over square root of LC. And so that's going to be 1 over the square root of 0.2 times 100, which is 0.22 radians per second. And at that resonant frequency, the current will be at its maximum value at that resonant frequency, and that maximum value will equal to the EMF maximum, which is 24 volts, divided by the resistance. So that would be 24 over 100, or it'd be 0.24 amps. So you see, if you actually operate at your resonant frequency, that is where your circuit is optimized for the frequency of the generator, then you get a much higher maximum current. So this is our maximum current in this circuit, but if it operated at the resonant frequency of 0.22 radians per second, it would have a much higher maximum current by an order of magnitude.